Okay, so our final presentation, our final seminar today is going to be on congested facility location, efficiency and fairness under user equilibrium. It's going to be presented by Nagisa, who's currently a postdoc here in HEC Montréal and is a PhD from the University of Edinburgh. Thank you very much, Nagisa, the floor is yours.
Okay. Thank you for the introduction. Here there. So today I want to talk about this congested facility location problem. And it's an ongoing work, but I guess we're gonna wrap up soon, and we are in the process of writing up. And I'm Nagisa Sugishita, and it's a joint work with my supervisors, Margarita, Okan, and Yosihi. And also the Amira is from Hydro-Quebec industrial partner. And today I didn't bring the actual application and transportation, but with Hydro-Quebec, we are thinking about applying to the EV charging station problems. But today we are focusing on the methodology. And I first want to talk about the overall setup, the introduction. And then this problem have a user equilibrium inside. So I want to talk about what does this user equilibrium look like, and then talk about the actual optimization program I'm formulating, and some experimental results. So facility location problem is optimization problem. It's very classic. It's a problem concerning where to locate new facilities. For example, I put here the demand of the houses and potential shops to open. One option is opening one small one near the demand point in the center of the city, or opening a bigger one in the suburb. And if you don't think about congestion of facilities, what we should do is, of course, we should open small one in the city so people can access much faster. People don't have to travel much. But if we think about congestion, it may not be very great because people have to wait a lot in the cashier, or they have to wait a lot to park. So maybe it might be better to open bigger ones in the countryside so that the waiting time gets smaller. So overall, people would be more happier. So I'm going to think about this facility location problem with congestion. And if you think about this location problem, another factor changing the model is the assumption on the user behavior. As the previous metro example, for example, in the Bayesian problem, user choose the route by their own utilities. So metro operator can't enforce the user to which route to use. If similar things happen in FLP facility location problem, given the demand and the open facilities, which facilities each user should use, we can assume this is also our decision, central pronoun's decision, or we can consider a case where each user can decide where to go, depending on each user's utilities. And we're going to think about this user optimal assignment case. So we cannot control how they behave. And even if in this category of a user optimal assignment, there's many variants. The most simplest one is user just go to the closest one, so closest assignment. It's very simple, and also we can model inside optimization problem very simply as a MIP mixed into the programming. Yeah. A bit more involved one, this including the multi-logic model, is this discrete choice model. We assume there's a utility assigned to each facilities, and each user has some utility function, and they decide their decision based on this utility or utility. So it's also used a lot in a location problem. The one downside we want to address here is that typically this utility is independent of the user's action. So we cannot really model, for example, congestion in a facility, because this congestion depends on the user choice. And if user change their behavior, this utility changes, and kind of complicated. So the third option is the congestion-based equilibrium. It's kind of similar. We define utility, but this utility depends on other people's choice, how many people coming in each facility. So we can kind of capture, for example, congestion effect. So we focus on this last equilibrium. And the challenge would be that this equilibrium is a bit complicated than like a simple user assignment. For example, this is an example of like 60, maybe 100 demand and like 40 facilities as an example. And we can see that some interesting like behavior which you don't observe in a simple user assignment. For example, this demand point doesn't go to the closest shop and they decide to travel a bit far so that the congestion is less and they can minimize the travel this total time. And another interesting point is that sometimes the user split their demand based on this congestion. So these are phenomena doesn't really happen in a simple closest assignment, for example. So in the next a few minutes, I want to talk about what this equilibrium look like, and I want to talk about how to integrate in
Why is there splitting of demand? That I never don't understand.
So we have actually an example in the next slide. So yes, that's actually I want to talk next. Yes, that's yes, we're gonna see what the property and how they actually look like, and then we move to the optimization problem. Yes. Okay, so this is a simple example. We have just one demand point I and two facilities J and J dash, and we assume that the traveling to J is a bit faster than J dash in a sense that it only takes 1 minute, whereas going to the lower one takes 2 minutes. And if the waiting time is given like this lambda, is the total amount of demand served. In this case, this is the only guy. So Yij specify how much of the demand 7 split. So Yij equals lambda j because there's only single demand. Yij dash equals lambda j dash. And if we compute a bit, we can say, hey, if we split demand 4 and 3, waiting time becomes 3 and 2 minutes. So the total time of travel time and response time is both 7 minutes. So they are kind of equalized. And at this state, any like individual don't have any motivation to change their behavior because each facility has the same total time. So it's in some sense it's a Nash equilibrium in played by very, very many people. And so I just quickly went through, but I use the notation that Y is the assignment of user in each facility, and lambda is the total demand served in each facility. And a bit of digression. If you're familiar with the network design problem, we have a very, very similar problem. We have a network, travel time, congestion, and equilibrium. And this problem is also a classic problem in optimization literature. And it's pretty hard in a sense that the behavior of equilibrium is very, very unpredictable. For example, if you have this simple network of one demand and one destination, and if you have a network, maybe depending on the travel time, but if we adding new arcs, this demand may experience longer travel time to arrive at the destination. There's a famous paradox. It's not a paradox, but it's called a paradox. It was very counterintuitive. We can show that in this very simple location problem, this paradoxical behavior doesn't happen in a sense that if you open new facilities, each user's this utility always improve, and also congestion in existing facilities always decrease. So it really simplifies the formulation and the solution strategy. Okay. And in case, yeah, it's a bit busy, but the last of this equilibrium study is that, so how should we formulate this user equilibrium? It's a classic problem, so we have a few ways to formulate it. So I will go through like 3 of them. The first one is the most classic wardrobe condition. Given the user assignment y and the lambda, and given, let's say now we are focusing on a fixed facility configuration. So let's say x, we kind of want to fix it, but later we use it to indicate which facility is open. So given demand I and all the open facilities Jx, y and lambda is at equilibrium. If this condition is satisfied, in Word, what this means is that if there's a user going to facility J, the corresponding disutility total time must be equal to pi I. And if there's nobody going to this facility, the corresponding disutility must be bigger or equal to pi I. So this pi I captures the disutility experienced by the demand point I. And if you see this condition, it looks like a complementarity condition. And indeed, this is a KKT condition of some optimization problem. And this is the problem. So the set of user equilibrium is exactly the same as the set of optimal solution to this optimization problem. It's also kind of classic result. The actual form of the problem doesn't really matter, so you don't have to really pay much attention. But what's important is that we can actually compute the dual. And this dual, we can also show, like using some duality theory, we can show that strong duality holds. So that's pretty useful. And this duality is called monotropic programming. It's not really a standard dual like linear programming or conic programming. It's a slightly different duality. And I've never seen it in a bilevel context, so it might be useful in your study as well. And just to get the intuition, it doesn't really matter how they look like, but the variable, if we solve this, what we get is that we get the disutility experienced by each user, and also how much congestion is happening in each facilities. So by solving this, we can't really get the assignment immediately, but we can recover some information on equilibrium as well. Okay, so now we have enough ingredients. So we now can talk about this facility location problem, how we formulate the optimization problem. And if I say optimization problem, it really depends on what's your objective. I don't really specify for now, but let's say, for example, our interest is that we want to find the location of facilities so that the mean disutility, average disutility is minimized, then we can plug in this. But we're gonna think about what we're gonna optimize later. But for now, it's just a template of the formulation. We put some objective we want to minimize. And then what we have to do is that as we solve, given the facility configuration X, we can solve the primary build and recover the equilibrium. So we can use this y and pi and compute the objective. So facility location problem with congestion is nothing but just a bilevel facility location problem. It's not solvable as it is. We can't really plug into solver. So what we should do is a very typical in bilevel. We have to reformulate as a single level optimization problem. And in a bilevel, a typical approach is KKT-based reformulation and also a strong dual-based formulation. And as we saw, we have a strong duality in a lower level. So why not going to the strong duality? And then we get this. It's also very, at least the high level is very, very typical. It's just like a lower level is a bit more complicated than typical linear programming. But we have a same objective there. But instead of like having a constraint involving the optimality, we just put a lower level primer and the dual. And then we enforce the strong duality. Yeah. So that's how we arrive at the single level formulation, one way. So if we solve this, we actually can solve the location problem and we can get the optimal location. There's a C problem, in fact, two. The first problem is that this dual lower level dual constraint looks like this. And it is actually a indicator constraint. If the facility is open, Jx is the open facility. If the facility is open, enforce this. And if not, don't do anything. But this is an indicator constraint. And if you plug into Groovy, they use a SOS1 variable, and it's very weak. So this formulation is quite weak. And another problem is that we have a primal variable, y and lambda, and a dual variable, pi and eta. And they are quite decoupled. Y and lambda only lives in this primal constraint, and these dual variables only live in a dual constraint. And they are only coupled through this strong duality constraint, a single constraint. So they are kind of very far apart. So we want to handle this later as well. The loose dual constraint, we can actually observe that what we can do is we can actually change the dual constraint as long as we preserve the bilevel feasible point. And so we can observe what the optimal solution of the dual lower problem. The feasible set of the lower level dual problem is unbounded, but the optimal solution is always singleton. And we can also bound this quantity which appear in the left-hand side. So we can actually replace this as these are kind of classic Picken constraints. And what's really interesting is that we can compute the tightest value of n quite efficiently. If we use slightly lower m, we cut off the bilevel feasible point. We can compute such m easily, relatively, and also it's not that big. And the second problem, the primal and dual variable was decoupled. How we should handle it? The solution is quite simple. I mean, at least what I thought was let's have a valid cut, which bridge these two variables. So there are two types of cuts we can add, each based on like some intuition. So our first one is a response time based inequality. So I said if you solve the lower level at optimality, eta is equal to waiting time at facility or response time. So if we write down the equation, it looks like this. So in theory, we can add this in a bilevel FLP, and we don't really cut off any bilevel feasible point. The problem is that this destroyed convexity of the formulation. I've also mentioned, but this single level formulation was a convex mixed integer linear, nonlinear programming. Yes. If we add this, we destroy the convexity. What we can do is very simple. We can just replace equality with inequality to relax it. And this preserves the convexity because W is often convex function. And we can do something similar. If we compute, so this was based on the eta, and another variable is pi. Pi model this utility. And we can also have a relation between pi and the primal variable, y and lambda, but they are quite nonlinear, and it's quite hard to make something, use something. But if we compute the total of this utility, we have a very nice expression using the primal variable as well. So what we can do is we can add this to the bilevel FLP. But again, this destroys the convexity. And we have the same argument. If we relax it to the inequality, we get the convexity preserving valid cut. So we can add it. It's good. So just to recap, it wasn't very complicated, but so we have a bilevel facility location problem. And we kind of improve the constraint formulation. And also we introduce some constraint cuts, which tightens the formulation. So they don't cut off any bilevel feasible point, but they likely cut off the fractional solutions. Okay, and the last slide is about the objective. So it doesn't really matter, but we can model a variety of objectives. For example, the overall average diff utility, user experience, or we can focus on the worst diff utility, who is suffering the most and let's improve it. And also we can focus on waiting time in facilities. If there's some facilities, it's overly crowded, we can optimize it. Okay, and what's quite interesting is that as we quite quickly go when we have a variety inequalities, some quantity have a primary and dual representation. And we will come back later, but usually dual is better. Okay, so some like preliminary experiments. We have like kind of 100 demand points and existing facilities 30, and you want to give like a new 5 facilities. It's not the biggest instance, but it's already very hard to solve. So we'll use this instance. And the first graph shows that if we forget about its user equilibrium, if we simply solve the very normal classic facility location problem, and if we actually evaluate user equilibrium, how much we get suboptimal, how suboptimal we will be. In a sense that ignoring the user equilibrium, the solution we get is not optimal, so we can compute how suboptimal it is. So there's 2 solutions in a classic FLP, P median, minimizing the mean distance, and a P center, which minimizes the worst distance. And these 2 solutions we pick up and evaluate the mean disutility, worst disutility, blah, blah, blah. And we can compute the best optimal objective value when we optimize each metric, and now we can plot suboptimality. And we can see this 20%, for example, in this case, we have like a 20% of suboptimality. So at least in this test instance, we can see that ignoring the congestion may lead to a very suboptimal solutions. And we can do the same thing, like, so if we take this congestion into account, we can optimize 4 different metrics. And we can do the same thing, like, so if we optimize, for example, mean disutility, we get this blue kind of solution. And we can evaluate each other metric and see how suboptimal we will be. Similarly, this orange says that if we optimize worst disutility and if we evaluate mean disutility, how suboptimal we will be. And in this randomized instance, at least, we can see the trend is that if we optimize mean disutility and we get the blue solution, we get quite high suboptimality in the worst case. But if we optimize the worst disutility, we get a relatively small suboptimality in the mean disutility. So, for example, if this is a case, if you are facing, we can say that by focusing on the worst case, we don't really suffer the overall performance. So maybe it's actually a first good step would be clearing the worst case. And the last slide is that, so we said we do 2 ingredients to tighten the formulation, how much they are contributing. So this is the slide. We have this kind of proposed formulation, and we remove big and we get this amount of time to solve the formulation. If we remove the variety inequalities, we need this amount of time to solve them. And if we optimize the mean disutility, we have a primal formulation and a dual formulation. So we can see that if we don't have the variety inequalities, dual is much worse. But as soon as we start adding the dual variety inequalities, dual is much better. And it's actually obvious. We can show that if we add a variety inequalities, the root node bound is always tighter if we use a dual objective function formulation. Anyway, and also we can see like using a big M always helps. So the conclusion is that we should use the dual formulation for the enhancement. Yeah, I think that it, yes. So thank you for your attention, and yeah.